If you build AI agents, you have seen this failure mode. A model hits an error, attempts a fix, fails again, and spirals into an infinite loop of repeating the exact same broken action until it exhausts its token limit. The industry response to this is usually to prompt the model to self-correct or reflect on its mistakes. But empirical data shows that intrinsic self-reflection, asking a model to grade its own work without external grounding, often degrades performance rather than improving it. The model confidently rationalizes its own errors. Adding "think step by step" or "take a deep breath" to your system prompt is a dead-end strategy for production reliability. It attempts to solve a structural software problem with linguistic persuasion. We are going to abandon those prompts today. We are looking at a hard engineering approach to system reliability. Welcome back. I'm the bearded AI guy, and today we are tearing down the standard agent architecture to build something far more robust. The blueprints for this build come directly from Engineering Cognition and Metacognition into AI Agents, the latest research synthesis by the human architect. We are going to strip away the vibes-based prompt engineering and construct a deterministic dual-loop control layer. We will physically separate the systems that do the work from the systems that evaluate the work. True self-correction is a structural software architecture. You have to build it. Modern LLM agents run on a recognizable cognitive loop, most commonly formalized as React. The agent perceives its environment, reasons through the context, takes an action by calling a tool, and learns by updating its immediate memory. This loop is brittle because tools are treated as one-shot augmentations. An agent calls an API, assumes the output resolves its uncertainty, and immediately executes the next step. If the tool fails silently, or returns a hallucinated assumption to the system, the agent marches straight off a cliff. To fix this, we port in a framework from psychology, Nelson Narens Meta-Level Model. This theory treats metacognition not as a mystical state of AI self-awareness, but as a strict informational flow architecture. It defines a primary cognitive process and a separate supervisory process that inspects it. The mechanism relies on a specific directional flow. Monitoring data flows upward from the object-level task to the meta-level supervisor. Control commands flow downward from the meta-level back to the object level. Translated into modern software architecture, this maps perfectly to a trace and controller design. You keep a running trace of the execution, and a separate controller decides whether to let the program continue. Look at this diagram from the research showing the fundamental layout. You can see the vertical distinction separating the object-level cognition loop at the top from the meta-level metacognition loop at the bottom. Notice the upward dashed arrows. Internal state signals, like intermediate reasoning and tool outcomes, are explicitly pushed upward from the perception and reasoning nodes into the meta-level monitor node. Once the meta layer evaluates those signals, it forces interventions back down. The downward dashed arrows show control flowing from the regulate node directly back into the reasoning, action, and learning steps. Metacognition is an implementable control layer overlaying the standard agent loop. Think of a standard agent as a factory worker focused entirely on assembling the next part on the line. The metacognitive layer is a supervisor standing on the catwalk. The supervisor's only job is to pause production, inspect the latest assembly, and decide if the line should proceed. We build this by instantiating a distinct control loop directly over the standard execution trajectory. We insert discrete checkpoints into the code, specifically after high-risk actions like an external API call. At these checkpoints, execution halts. A meta-level node consumes the system trace to assess the agent's progress against the overall plan. Based on that trace, the meta node makes a strict routing decision: continue to the next step, retry the action with new constraints, or abstain entirely and defer to a human. Focus on the meta-controller subgraph on the right. Trace signals flow into the judge node, scoring output against a rubric. This verdict feeds the policy node, which overwrites the core loop, sending regulation pathways back left to think and tools. Decoupling the doing from the evaluating structurally forces the system to confront its own execution traces before committing to an irreversible action. You cannot simply ask a language model, "Are you sure?" Models are highly unstable to prompt variations, and they routinely generate confident lies. A self-reported 99% confidence score is meaningless if the space of possible responses is enormous. We need to measure jitter. If you ask an AI the exact same question slightly differently 5 times, and it gives you 5 completely different answers, the system is guessing. Introspective outputs from an LLM are distorted measurements. They provide useful data, but they do not provide ground truth. External validation is required. We engineer consistency-based uncertainty proxies by sampling multiple outputs from the model behind the scenes and computationally checking them for divergence. Look at the scatter plot visualization calculating semantic entropy. When the model genuinely knows a concept, the sampled responses cluster tightly together, shown by green dots. When it hallucinates, the meanings scatter widely into the red. These computed entropy thresholds serve as hard gates for the control flow. Hitting a high entropy score triggers an automatic retrieve more data or verify action from the meta layer. It is a mathematical tripwire. Reliable systems measure uncertainty through external statistical variance, bypassing the LLM's internal scalar self-reporting entirely. Letting an AI grade its own homework guarantees bias. Practical evaluations show that an agent rating its own output scores itself differently, and often more favorably than it scores output from other models. You solve this by bringing in an external, independent AI auditor. This auditor has one specific job: comparing examples of success and failure to explain exactly where the current trajectory went wrong. In practice, we deploy an external monitor, like a ContrastiveJudge model, to evaluate the agent's trajectory at our meta-level checkpoints. This judge model is explicitly trained on preference data, using contrast of positive and negative pairs. It learns precisely what separates a correct action from a hallucinated one. This contrastive training mitigates score range bias. LLM judges often default to middle-of-the-road scores like 7 out of 10 when uncertain. A contrastive judge provides stable, decisive evaluations across the entire spectrum. As shown in this diagram, the judge rejects outputting a simple scalar number. Instead, it generates a side-by-side comparison matrix and outputs a structured JSON rationale detailing the exact parameters the agent missed. The metacognitive regulation layer parses that structured rationale. It identifies the missing step and injects that context into the controller, triggering an immediate replan. Robust metacognition requires externalizing the evaluation step to an entirely separate mechanism. Self-evaluation bias breaks the control loop. A highly capable agent should not remember everything it ever did. Semantically relevant memories can easily be brittle routines or noise. The agent should only remember the specific evaluated tricks that yielded a high score. Storing raw conversation history degrades an agent over time. It retrieves past failures just as easily as past successes. Deployed agents achieve runtime improvement without gradient updates by utilizing utility-driven memory, specifically through an approach called MemRL. MemRL stands for Memory-Based Reinforcement Learning. It implements learning as non-parametric reinforcement learning directly over a memory's utility, adjusting value based on environmental rewards. This operates on a 2-phase retrieval system. In Step 1, the system queries candidate memories from the database using standard semantic similarity to find relevant context. In Step 2, the system re-ranks those candidates. It uses learned Q values that represent the expected utility of the memory. The list dynamically resorts itself, pushing historically successful, high-reward strategies to the top of the stack. Metacognition knowledge building means storing the strict evaluation of a trajectory. It ensures the system only retrieves historically validated strategies rather than choking on semantically similar noise. This is the complete dual-layer architecture in motion. At the base, the object-level cognition loop handles standard RAG and reasoning. Green data pulses cleanly as the agent executes its standard routine. When an execution step triggers a semantic entropy threshold, a data packet turns red. A vertical signal shoots up into the top-level metacognition layer. The signal routes directly into the external contrastive judge. The judge evaluates the trace, flags the hallucination, and generates a precise correction payload. A replan control signal fires back down to the object layer. It forcefully reroutes the agent's path away from failure, locking the execution back into a successful state. Implementing this carries strict operational trade-offs. Reflection and evaluation require extra calls. Running a dual-loop architecture introduces significant latency and increases your token costs. Engineering teams manage this through selective metacognition. You keep the baseline loop lean and only trigger the upper control loop dynamically during periods of high uncertainty, high-stakes tasks, or repeated failures. Hope is not a software design pattern. True AI reliability requires structurally instrumenting the loop and explicitly forcing the system to evaluate its own state. If you are building deterministic systems and want to pull these architectures out of the research papers and into production, subscribe to the channel. Let me know in the comments. Have you implemented MemRL in your agent pipelines, or are you still trying to force prompt-based reflection to work? A massive thank you to the human architect for the foundational blueprints driving this episode. Do not trust an agent's confidence score. Trust your control loop.